This discussion centers on a novel computational framework introduced by Christopher Young in his January 2025 paper titled Entropy Resolved Resonance Profiles, Non-Iterative Mathematics. The purpose of this work is to present a universal, non-iterative method for solving complex numerical problems across physics, computation, and mathematics. Unlike traditional iterative or probabilistic methods, this approach leverages a fixed entropy-weighted transformation that filters system states through harmonic resonance, directly selecting stable solutions without incremental approximation. The background to this work lies in the widespread reliance on iterative techniques, such as gradient descent, stochastic sampling, or path integral computations, across many scientific domains. While effective, these methods typically require stepwise refinement, convergence monitoring, and often significant computational resources, especially in high-dimensional or chaotic systems. The objective here is to replace these iterative processes with a resonance-based framework that projects candidate states onto their stabilized configurations in a single deterministic pass. At the heart of the framework is a universal mathematical operation expressed as m of x equals f of x times e raised to the power e to the power of e of x minus e naught. Here, f of x represents the raw functional behavior of the system. This could be energy, cost, or wave amplitude, while e of x quantifies the deviation from a global resonance baseline e naught. The parameter beta, greater than 0, controls entropy selectivity. This double exponential damping sharply suppresses states that deviate from harmonic balance, effectively filtering out unstable or non-physical configurations. The paper formalizes this core operation as a resonance entropy filtering process, defining an entropy modulation function s of x, x equal to e, raised to e of x minus e naught. The transformation m of x becomes f of x times e raised to s of x. Since s of x approaches 1 when e of x equals e naught, and rapidly approaches 0 otherwise, the method isolates the harmonically balanced contributions of the system's raw function. This framework is rooted in what the author terms harmonic resonance number theory, viewing numerical states as wave-like entities characterized by intrinsic frequency and phase. Each state is modeled as a resonance field R of x defined by amplitude, frequency, and phase. The stabilized output m of x is then interpreted as the resonance pattern filtered by entropy-based damping, yielding a standing wave centered on the most energetically balanced configuration. A key structural element is a fixed resonance weighting kernel, a set of 5 weights, approximately 0.602, 0.172, 0.205, and 0.054, and 0.019. These weights ensure that composite resonance interference fields are self-stabilizing across all variants of the method. When combining component resonance states, the filtered resonance is a weighted sum of harmonically modulated functions derived from the input state structure. The paper establishes a fundamental theorem called the entropy convergent resolution theorem. It states that for any bounded differentiable function, f of x and convex energy functional e of x with a global minimum at e naught, the transformation m of x converges to f of x if and only if e of x equals e naught. Otherwise, m of x tends towards 0. The proof relies on the double exponential decay suppressing all non-minimum energy states, so only minimum energy states persist, stabilizing the solution non-iteratively. A corollary of this theorem applies to quantum mechanics, showing that quantum superpositions can be resolved deterministically without probabilistic collapse. Given a quantum superposition with component states each having energy E sub n, applying the entropy resolved profile yields a filtered state where only the component with minimum energy survives in the limit. This replaces stochastic collapse with a deterministic resonance selection. The first application domain explored is dynamic stability, focusing on nonlinear and chaotic dynamical systems traditionally solved by iterative time stepping. The framework reformulates the problem by defining the stabilized state m of x as the system function f dyne of x multiplied by the entropy filter. The energy functional E of x is defined as a measure of oscillatory energy, combining squared dynamic force and variance to quantify deviation from equilibrium. By minimizing E of x, the method directly computes the system's long-term attractor without simulating intermediate states. An example given is the logistic map, a classic nonlinear system defined by x sub n plus 1 equals r times x sub n times 1 minus x sub n. Using the entropy-resolved approach, the method isolates stable fixed points or cycles directly by suppressing unstable oscillations through the entropy filter. For instance, at r equals 3.2, where the logistic map exhibits a 2-point attractor, the approach extracts this cycle without iterative simulation. A formal theorem, called the non-iterative attractor resolution, guarantees that the entropy-filtered state converges to a fixed point satisfying the dynamical map's equilibrium condition and minimum energy. This approach thus acts as a deterministic attractor resolver, projecting any initial state onto the stable equilibrium branch, even in chaotic or multi-stable systems. For a physical example, the damped harmonic oscillator equation is considered. By defining the energy functional as the sum of acceleration and velocity terms squared, the entropy-resolved profile returns the motionless rest state directly without simulating the decay process over time. The second major variant applies the framework to global optimization problems. Instead of conventional iterative descent methods, the method identifies the global minimum of an objective function L of x by applying the entropy-weighted resonance selection to L of x itself. The transformed function m of x equals L of x times e raised to L of x minus L naught, where L naught is the global minimum. This suppresses all non-optimal candidate values sharply, isolating the global minimizer in a single evaluation pass. An example function illustrating this is a quartic polynomial with both local and global minima. The entropy filter eliminates local minima contributions, enabling direct recovery of the global minimum without gradient or Hessian computations. Theoretical guarantees ensure that as the entropy parameter increases, the transformed function converges to zero except at the global minimum. The approach extends naturally to discrete domains, such as integer programming, Boolean satisfiability, or combinatorial optimization problems like the traveling salesman problem. By evaluating the entropy-weighted function over candidate solutions, the global optimum emerges without iterative search or stochastic heuristics, reducing computational complexity. A corollary, the non-iterative optimization principle, states that for finite domains and bounded objective functions, the global minimum can be found in one pass through the entropy-resolved transformation. The third variant addresses quantum state computation, where traditional methods rely on probabilistic interpretations, stochastic sampling, or path integrals. Here, quantum states are represented as resonance patterns, with each eigenstate corresponding to a harmonic component characterized by amplitude, frequency, and phase. The entropy-resolved framework replaces probabilistic collapse with deterministic filtering based on energy deviation. The quantum wave function, expressed as a superposition of basis states with complex amplitudes, is transformed by applying the double exponential energy filter. This exponentially suppresses all states except the one with minimum energy, yielding a deterministic selection of the physically realized quantum state. An application to the Wheeler-DeWitt equation in quantum gravity is presented. Traditionally requiring infinite path integrals over geometries, the framework replaces this with a filtered resonance profile that collapses non-physical geometries by entropy weighting. This yields a non-iterative, exact approximation to the quantum gravitational wave function without integral evaluation. The deterministic nature of this quantum state selection is formalized in a theorem stating that in the limit, the resolved wave function converges to the eigenstate corresponding to the minimum energy. This provides a collapse-free interpretation of quantum measurement where outcomes arise from harmonic energy minimization rather than stochastic processes. An example of quantum interference selection illustrates how a superposition of two states with slightly different energies resolves deterministically to the lower energy state as the entropy parameter increases. The fourth variant focuses on transcendental constant resolution, targeting numbers such as pi, e, and natural logarithms that cannot be roots of polynomial equations with rational coefficients. Conventionally, these constants are approximated via infinite series or continued fractions. The entropy-resolved approach models transcendental numbers as irreducible resonance states in harmonic systems, non-repeating, phase-stable interference patterns without algebraic factorization. The method constructs finite weighted sums of frequency-modulated functions such as powers, exponentials, or sinusoids with fixed harmonic weights. This finite harmonic sum approximates transcendental constants to near machine precision without iteration. An example is the natural logarithm of 2, which is computed as a weighted sum of logarithms of shifted arguments, yielding 6-digit precision instantly. The entropy weighting acts as a resonance lock, stabilizing against numerical drift. A theorem guarantees that any transcendental constant expressible as a convergent series can be approximated to arbitrary precision by a finite harmonic sum with fixed weights, without iterative computation. This supports a physical interpretation of transcendental numbers as unique attractor points in resonance space, distinct from algebraic numbers. The framework also applies to pi, constructing a weighted sum of arctangent functions with selected arguments and fixed weights to achieve 67-digit accuracy rapidly, far surpassing traditional series convergence. The fifth variant deals with physical constant refinement, such as the fine structure constant, Planck's constant, and the gravitational constant. These constants are treated as stabilized harmonic features of the vacuum, emerging from standing wave structures and resonance equilibria across multiple energy modes. The computational framework expresses constants as finite sums of universal harmonic weights multiplied by dimensionless harmonic functions derived from vacuum scaling ratios, logarithmic relationships, or physical ratios. Entropy filtering can be optionally applied for ultrafine stability. For example, the inverse fine structure constant is approximated as a weighted sum of logarithms of selected positive numbers, chosen to reflect harmonic ratios involving fundamental constants and vacuum energy distributions. This yields 6-digit accuracy matching current codata values without empirical measurement. The approach interprets vacuum energy density and characteristic resonance length scales as governing oscillation equations whose resonance structure determines constants like Planck length, cosmological constant, and gravitational constant. Thus, these constants emerge naturally as harmonic attractors stabilized through entropy weighting. A theorem formalizes that any physical constant derivable from vacuum resonance equations can be approximated by a finite harmonic sum within any desired precision, with entropy filtering ensuring selection of physically relevant configurations. An example for Planck's constant expresses it dimensionlessly by normalizing against vacuum resonance parameters and computes it through a weighted logarithmic sum, producing high-precision values consistent with observations. The paper concludes by unifying these 5 variants under a single field theoretic computational framework. The central operator, applying entropy-weighted resonance filtering, acts as a universal field projector mapping raw system dynamics into stabilized solution spaces. This projection defines a geometric contraction mapping on a harmonic resonance manifold endowed with an entropy-induced metric. Entropy weighting functions as a built-in computational gradient that suppresses unstable states, eliminating the need for iterative convergence checks or path tracking. Computation thus becomes a deterministic evolution on a structured resonance manifold rather than an adaptive search. This generalization elevates computation from stepwise symbolic operations to equilibrium computations of structured resonance fields filtered by entropy. The framework can be viewed as a non-iterative computational field theory defined over harmonic entropy manifolds. In summary, the paper's key contributions include the introduction of a mathematically unified, physically grounded framework for deterministic, non-iterative numerical resolution across diverse domains. The approach replaces iterative procedures with a resonance selection process governed by entropy-weighted energy minimization. Broader implications suggest a deep connection between numerical computation, physical structure, and harmonic energy propagation. This hints that the foundations of mathematics may themselves be resonant, and that numerical tools are beginning to reflect this intrinsic geometry. Future directions proposed include extending the harmonic manifold model to discrete logic and formal systems, connecting the approach to geometric analysis methods such as Ricci flow for topological inference, simulating multi-field entropy collapse in quantum cosmological contexts, and applying entropy-resolved resonance profiles to symbolic AI architectures as alternatives to stochastic training. Collectively, these developments point toward a unified framework integrating computation, cognition, and physical law, wherein entropy, resonance, and structure form the foundational principles.